Welcome back, ladies and gentlemen. Today's topic, still in section 10.1, day 2, talking about tangents again, but this time about properties of tangents. Before I get into the slideshow again, I am going to skip right over to Geometry's Sketchpad to show you a couple things. The first thing I'm going to do is I'm going to construct a circle. Then I am going to construct a radius of that circle, just by connecting those 2 points there. And then remember that all I need to draw a perpendicular line is a line and a point. So I'm going to tell the computer that I want that line and that point, and I would like a perpendicular line through that point. And please make that for me. So I'm going to go down there and select perpendicular line. And you'll notice something kind of interesting. This perpendicular line that I just constructed, it's a fairly special line. Look at it. It's a vocab word from yesterday. That line that I just constructed intersects this circle at exactly 1 point, making it a tangent line. So this is kind of a cool property of tangent lines, is that their point of intersection, the point of tangency, if you connect that point to the radius, it forms a perfect 90-degree angle every single time. The second thing I'm going to do this drawing is simply make another radius, just like that. And I'm going to do the same thing, except I'm going to construct another perpendicular line from that point, just like so. And you'll notice it creates another tangent line, and furthermore, those two tangent lines intersect at a point right there. Now, that will always happen no matter how I move these points around or stretch the circle, or how big of an arc I make, or even if I bring it around there, they will always intersect in one place unless I make those two lines parallel. So then I'm going to highlight both these points and I'm going to ask the computer to measure that for me. Guess what? If I do that on that side and do it on this side, they not only look equal, but they are equal every single time, no matter how I manipulate the drawing. And those are our two theorems today. Basically, our theorems today say that if you draw a tangent line to a circle, that a radius is perpendicular to it. And if you have two tangent lines that intersect at a point, then the two tangent segments that go from the point of tangency to that point are equal to each other. So it forms a kite, more or less, because these radii are equal by definition. And then these two segments are also equal. To the slideshow. Here we go. There are your official theorems for the day, Theorem 10.1 and 10.2. Now they say exactly what I just demonstrated, and what is interesting about Theorem 10.1 is it is an if and only if statement. So that means that you can prove that a line is tangential if you can show that it's 90 degrees, and if you can show that that's 90 degrees, then it is tangential. So it works both directions, and it should be very useful to you. And then secondly, tangent segments from a common external point. So if you basically, it's the opposite of the way that I constructed it. We constructed it tangent lines first, and then we found that point. But if you take any point outside the circle and draw tangent lines to the circle, then those two lines that you draw are congruent. So we can use these properties to do a couple simple to slightly less simple problems. Here's an example where we have an external point drawing to two tangent segments, and we know that those two tangent segments should be equal. So this one's a very simple two-step equation. Like most geometry problems, if you see two expressions and nothing else, might as well try setting them equal to each other and solving for x, and that's exactly what you do here to get x equals 8. The next example is slightly more complex, and it's asking you simply, is ST a tangent segment? If it were a tangent segment, what would be true? Well, if it were a tangent segment, then this angle right here, STP, would be a right angle. And if STP were a right angle, then triangle STP would be a right triangle. And if STP were a right triangle, then it would satisfy the Pythagorean theorem. So what we have to do here is we have to plug in these three numbers and see if they satisfy the Pythagorean theorem. So plug them in. These are your two legs, 35 and 12. 35 squared plus 12 squared. Notice the use of the question mark over the equal sign because I'm not sure yet. And then once I've verified that it is indeed equal to 1369 on both sides, then I can check it off as being true. Therefore, ST is a tangent segment. Last example for us today. It tells us that AB right here is a tangent segment, and they're asking for the radius of the circle. So 50 feet goes from here to the outside edge of the circle. Well, again, if AB is a tangent line and we're given that, then we know that ABC, the triangle ABC, is a right triangle, and thus all these dimensions should fit the Pythagorean theorem. So that progression of it must be a right triangle, or a right angle, must be a right triangle, and must satisfy the Pythagorean theorem all fall in line just like before, except one of our sides, our hypotenuse, has two terms to it. So our hypotenuse is 50 feet plus r feet. So we just have to substitute that into the Pythagorean theorem properly with a set of parentheses. And because I saw it so many times on that solving square roots worksheet, I'm going to tell you and plead and beg with you, please do not distribute this power of 2. This is a binomial squared. You need to FOIL it. And if you do that, the next line looks like that. 80 squared is 6400, r squared is r squared, and once you FOIL that and combine like terms, you get r squared plus 100 plus 2500. From there, we have an r squared on both sides. That's nice. We don't have to solve a quadratic anymore. They're just gone. And then it's simply combining like terms and solving. 39 feet equals r. Here's your assignment for the lesson. I'll see you next time.